Welcome back to the deep dive. You know, I had a bit of a moment this morning.
Oh, yeah.
I picked up my phone, glanced at it, and it unlocked. I didn't press a button, didn't type a code.
Yeah.
It saw me. And it struck me that we have completely normalized something that is, frankly, miraculous.
It really is. We treat it as this mundane utility, unlocking phones, backing up cars without hitting the garbage can. But what's actually happening under the hood is, well, it's one of the most complex challenges in computer science.
And that is exactly what we are unpacking today. We're doing a deep dive into machine vision.
Mm-hmm.
And I don't just mean cameras taking pictures. I mean, how do we get a slab of silicon, which fundamentally only understands ones and zeros, to look at this chaotic, messy world and actually understand what's happening?
It's a massive topic. And if you look at the source material we've pulled together, it's everything from biological studies of frog eyes to the math behind autonomous driving. The one consistent theme is that seeing is just incredibly hard work.
See, that's funny to me because I open my eyes and boom, there's a coffee cup, there's a microphone. It feels instant. It feels, free.
For you it is, but for a machine, that boom is a mathematical nightmare. And to understand why, we have to start with probably the most important distinction in the whole field.
Okay.
The difference between sensing and perception.
Okay, let's unpack this because I think most people, myself included, probably use those words interchangeably.
They do, but they are worlds apart. Sensing is just measurement. A camera sensor is just a device that measures light intensity. If I handed you a spreadsheet with 10 million numbers on it representing pixel brightness, that is sensing. It's just raw data.
And it's just a grid of values, no meaning.
Exactly. Perception, on the other hand, is the interpretation of that data. It's looking at that spreadsheet of 10 million numbers and saying, oh, that pattern of numbers, that's a tiger, run.
So sensing is there is light hitting this pixel, and perception is I am about to be eaten.
Precisely. Perception is all about turning that raw, unwashed sensor data into information an agent can actually use to act. And the sources highlight this massive problem right out of the gate called sensor model ambiguity, or as I like to call it,
The Godzilla problem.
the Godzilla problem.
I love this example in the reading. It basically asks, looking at an image, is that a plastic toy monster on your desk? Or is it a 300-foot lizard destroying a city?
And here's the kicker. To a computer, those two things can generate the exact same grid of numbers.
Wow.
If the geometry aligns perfectly, a small object close up produces the exact same image on the retina or the sensor as a massive object far away.
That is wild. I mean, we solve that instantly because we have common sense. We know Godzilla isn't real. We know toys are small.
Right. We have priors. We have a lifetime of context. A computer doesn't actually have that. It has to mathematically resolve that ambiguity, and it has to do it while processing a staggering amount of data. One of the papers mentioned that a standard robotic video feed can generate something like 10 gigabytes of data per minute.
10 gigabytes a minute. That is just a fire hose of information.
It is. So the real mission of machine vision isn't just what is this, it's what can I safely ignore? If a robot tried to process every single pixel with equal importance, its brain would just melt.
So perception is as much about filtering as it is about seeing.
I think it's mostly about filtering.
Okay, so before we get to the filtering and the AI brains, let's talk about the hardware. How does the image actually get into the machine? The physics of it. The sources start with the absolute simplest model, the pinhole camera.
The classic camera obscura. This is physics 101, but it's so crucial for the math that follows.
Right.
Imagine a light, tight box with a tiny, tiny pinhole on one side. Light rays travel in straight lines, they pass through that little hole, and they project an image on the back wall.
And because of the geometry, that image is upside down and backward, right?
It is, but the important part is the math it creates, which we call perspective projection. This is basically the rule book for how our 3D world gets squashed into a 2D image.
This explains why parallel lines, like railway tracks, look like they touch in the distance.
Exactly, the vanishing point. In the real world, those tracks never meet. But in the image, they converge. And distant objects look smaller. It sounds obvious to us, but the computer has to learn to reverse engineer this. It has to understand that if the pixels of the railway tracks are getting closer together, the tracks aren't actually bending, they're just receding into the distance.
So if pinholes are so simple and mathematically perfect, infinite depth of focus, perfect geometry, why don't we use them on our phones? Why do we pay hundreds of dollars for these fancy glass lenses?
2 reasons: light and sharpness. A pinhole is just a brutal trade-off. If the hole is tiny, yeah, everything is in focus, but the image is incredibly dark because almost no light gets in.
Okay, so just make the hole bigger.
But if you make the hole bigger without a lens, the light just sprays everywhere. You don't get an image, you just get a blurry mess. So we use a lens. The lens lets us have a big opening, an aperture, to gather lots of light while bending all that light back to a sharp point on the sensor.
But there's a catch, isn't there? Because now we have to deal with focus.
Correct. Lenses introduce what's called depth of field. Only objects at a very specific distance are perfectly sharp. Everything else gets blurry.
Which is why my portrait mode photos look cool, but it adds another layer of complexity for the computer. Now it has to deal with blurry data if things aren't at exactly the right distance.
It does. And then you layer on the complexity of lighting. The notes bring up Lambert's cosine law, which sounds intense, but it's actually really intuitive.
Lay it on me.
It basically just explains shading. Why does a ball look round in a photo?
Because of the shadows.
Right. It's because the brightness of any surface depends on the angle of the light hitting it. If a surface faces the light directly, it's bright. As it curves away, the light hits at a glancing angle, so it gets darker.
So the computer looks at that shading, that gradient from light to dark, and it calculates, the surface is curving away from me.
Exactly. It's using brightness to infer shape.
Yeah.
And then finally, you add color. The principle of trichromacy.
This is the whole RGB thing, red, green, blue.
Yes, and it's really a bit of a biological hack. We humans only have 3 types of color receptors for red, green, and blue. So our screens and cameras only need to use those 3 colors to trick us into seeing everything from neon pink to burnt orange.
But the source mentioned the mantis shrimp, which I found hilarious.
Oh, the mantis shrimp totally exposes our arrogance. It has 12 types of color receptors.
12.
12. If we wanted to build a TV for a mantis shrimp, an RGB screen would look like garbage to it. It would be colorblind. It sees colors we can't even imagine. But, since we build machines for humans, we stick to the 3-color model.
Okay, so we've got the image. It's focused, it's lit, it's in color. But to the computer, it's still just the soup of pixels. We need to start finding some structure. The reading calls this early vision.
This is where we stop doing physics and start doing data science. And the first step is almost always finding edges.
Which seems easy.
Yeah.
An edge is just where the dark table ends and the white wall begins, right? A sharp change in brightness.
In a perfect world, yes. But the real world is messy. Sensors aren't perfect. They have noise, random static. If you just tell a computer find every change in brightness, it's going to highlight every speck of dust and every little grain of sensor static.
It would just look like static on an old TV. You wouldn't see the table, you'd just see fuzz.
So we do something that sounds completely counterintuitive. Before we look for edges, we actually blur the image.
Wait, what? We just bought that expensive lens to get a sharp image, and now the first thing the computer does is blur it.
We blur it mathematically. It's called Gaussian smoothing. Think of it like squinting your eyes. When you squint, all the tiny details, the noise, they disappear. But the big shapes, the table, the door, the person, they remain.
So you wash out the noise so the real edges can stand out.
Exactly. You sacrifice a little bit of fine detail to find the true structure, but even that isn't foolproof. The sources bring up what they call the leopard problem.
Right. If you run an edge detector on a leopard, you don't get a leopard. You get a million little circles.
You get the spots, but you completely miss the cat. The edges are actually misleading there. This is where texture analysis comes in.
Okay.
The computer stops looking at individual lines and starts looking at statistics. It sees a repeating pattern of orientations, spot, 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 and realizes, hey, this whole area has the same texture. It's probably one object.
So it's grouping things by their statistical pattern, not just their outline. That's clutter.
It is. It's sort of akin to how you recognize a gravel road. You don't look at every single rock. You just recognize the overall texture of gravel.
So now we have objects. We have edges and textures. But the image is still flat. It's 2D. If I'm a self-driving car, knowing there's a flat picture of a truck isn't enough. I need to know where it is. I need that third dimension.
This is the reconstruction problem. How do you get 3D from 2D? The material outlines 3 main ways, or cues. The first one is pure movement, motion parallax.
This is the train window effect.
Perfect analogy. If you look out a train window, the bushes right next to the track are just blurring past at high speed. The mountain way off in the distance looks like it's barely moving at all.
So the speed at which something moves across your vision tells you how far away it is.
That's optical flow, and biology loves this. The source highlights the fruit fly, Drosophila.
The little guys on the bananas.
Then they have these tiny brains. They can't build a complex 3D map of the kitchen, but they use optical flow if they see a pattern expanding really, really fast in their field of view.
It means they're about to smack right into it.
Right. Rapid expansion equals time to contact is very short, so they reflexively adjust their wings. They don't know what the object is. It could be a wall, a fly swatter, your hand,
Yeah.
but they know the geometry says move.
That is wildly efficient. It's survival geometry. But humans and more advanced robots, we use something better. We have two eyes.
Stereopsis. This is really the gold standard for depth. Because our eyes are separated by a few centimeters, they see the world from slightly different angles.
Yeah, I can see this. If I hold my finger up and close one eye then the other, the finger seems to jump.
That jump is called disparity. If an object is close to your face, that jump is huge. If it's a mile away, the jump is tiny. The brain, or the computer, measures that disparity to calculate the exact distance.
There was a stat in the reading that just blew my mind about how sensitive this is.
It is incredible. At reading distance, say, about 30 centimeters, humans can detect a depth difference of just 0.036 millimeters.
That's barely the width of a human hair.
It's why you can thread a needle. That tiny variance between the left eye image and the right eye image is enough for your brain to triangulate position with sub-millimeter precision. And self-driving cars use stereo cameras, literally 2 cameras mounted side by side to do the exact same thing.
But what if you aren't moving and you only have one camera? There's a third cue mentioned. Just context.
The ground plane assumption, this is pure logic. The computer basically assumes that gravity works and that things generally sit on the ground.
So it looks for where the object meets the floor.
And it uses the horizon trick. If a computer recognizes a pedestrian in the image, it checks where their feet are relative to the horizon line. If the person looks huge, taking up the whole screen, but their feet are way up near the horizon,
Then either they are floating or they are a giant.
a 50-foot-tall person standing 5 miles away. And since that's impossible, ignoring our Godzilla friend from earlier, the computer knows something is wrong with the data. It uses the geometry of the world to sanity check what it sees.
Okay, so we've reconstructed the space. We know where things are.
Yeah.
Now for the Holy Grail. Knowing what things are. Is that a mailbox or is that a child?
This is recognition. And for a long, long time, the dominant technique was the sliding window.
Which is exactly what it sounds like.
Pretty much. The computer takes a small virtual box and it just drags it across the image pixel by pixel. At every single stop, it runs a test. Is this a face? Is this a face? Is this a face?
But what is this a face actually mean in math? It's not looking for a nose and eyes like we do, is it?
Not exactly. For things like pedestrians, it uses something called HOG features.
Histogram of oriented gradients.
A terrible name for a really brilliant concept. Don't think about colors because lighting changes colors all the time. A red shirt can look black at night,
Right.
but gradients, the change from light to dark, are robust. A standing person has a very specific shape. Vertical lines for the torso, maybe a circular curve for the head.
The source called it the lollipop shape.
Or scissors if the legs are walking. The computer looks for that specific arrangement of gradients, that lollipop or scissor signature. It doesn't care if you're wearing a tuxedo or a swimsuit. It cares that the flow of the gradients matches the statistical model of a human.
But humans are flexible. We aren't rigid lollipops. We do jumping jacks, we ride bikes, we curl up in balls. How does it handle that?
That requires a step up in complexity. It's called structural recognition. The source calls this the cardboard people model.
I loved this visual. It treats a human like a paper doll.
Exactly. Imagine cutting out rectangles of cardboard.
Right.
One for the forearm, one for the upper arm, one for the torso, and you pin them together at the joints.
So the computer has a model of these rectangles and how they all connect.
It has a spring model. It knows the hand is connected to the arm and the arm to the shoulder. It knows the head should probably not be attached to the foot.
So if it sees a head shape near a foot shape, but nobody in between, it just says, that's not a person.
Right. It helps solve for occlusion, when parts of the body are hidden behind a car or a tree. It fits this pictorial structure to the image, trying to find the best arrangement of those rectangles that matches the pixel data. It lets the machine track a person, even if they are in some weird yoga pose.
So putting this all together, we have pinholes, edge detection, stereo vision, cardboard people. The biggest application for all of this right now has to be the self-driving car.
It's the ultimate final exam for machine vision. Because the stakes are, well, life and death.
How do they layer all these systems?
They use everything we just discussed, but simultaneously. For lateral control, So staying in your lane, that's pure edge detection. It's just finding the high contrast edge between the white paint and the gray asphalt. That's how it steers.
Simple like that.
For longitudinal control, not rear-ending the guy in front of you, it's using stereo vision or optical flow to measure the distance and the expansion rate of the car ahead.
But there was a specific problem mentioned called drift. This idea that the robot can get lost even if it knows how fast it's moving.
Visual odometry.
Yeah.
Yeah, imagine you walked blindfolded and just counted your steps. I've taken 100 steps, so I must be 100 meters away.
Okay.
But if your stride is off by just a tiny bit or you slip on some ice, that error just accumulates. After a mile, you might think you're on the road, but you're actually in a ditch.
So how do they fix the drift?
They use landmarks. The car has a map. It sees a stop sign or a specific building corner. It recognizes it and says, I see the post office. I thought I was at meter 500, but I'm actually at meter 502. It resets its position.
It's constantly correcting its own hallucinations of where it is.
That's a great way to put it. And that brings us to the really interesting philosophical lesson the sources ended with. The frog.
What the frog's eye tells the frog's brain. This is a classic study, right?
It is. And it turns out a frog's vision is not a general-purpose camera like ours. It is biologically hardwired to see one thing: small, dark, moving spots. Bugs.
And if the bug doesn't move?
The frog is blind to it. A frog will literally starve to death sitting in a pile of freshly killed flies. Because they aren't moving, the frog's brain doesn't classify them as food. It doesn't even classify them as objects. It's just background noise.
That sounds like a massive design flaw.
Or is it perfect engineering?
Yeah.
The frog doesn't need to appreciate the sunset or the texture of the moss. It needs to eat and not get eaten. Evolution has optimized its vision to compute only what is necessary for survival.
And the argument is that robots should be more like frogs.
Exactly. A self-driving car doesn't need to understand the architectural style of the bridge it's crossing. It doesn't need to know if the pedestrian is happy or sad. It just needs to know obstacle, location, speed.
Efficiency over completeness.
Right. Don't try to reconstruct the entire universe. Just reconstruct enough to make the right decision.
It's fascinating to think that we started this conversation talking about pixels and math and somehow ended up at evolutionary biology.
It's all connected. We are, in essence, trying to reverse engineer millions of years of evolution in just a few decades of code.
So, to recap, we grab light through a lens, project it onto a sensor, blur it to remove noise, hunt for edges, compare the view from two eyes to find depth, and then we fit cardboard models to the shapes to figure out if it's a person or a mailbox.
And we do it all 60 times a second while moving at 70 miles per hour.
When you put it that way, it's a miracle it works at all.
It really is. But I want to leave you with one final thought. We talked about priors, the assumptions machines make, like roads are flat or people have two arms.
The mental models they use to make sense of all the chaos.
Right. There is this really delicate balance between the data, what the camera actually sees, and the prior, what the machine expects to see.
Okay, here's where it gets really interesting.
If a machine relies too much on its prior, if it believes its internal model more than the actual sensor data, at what point does it stop perceiving reality and start, well, creating its own?
You mean literally hallucinating?
Exactly. If a self-driving car encounters a massive pothole, but its prior says highway roads are perfectly flat, it might simply delete the pothole from its perception. It won't see it because it believes it shouldn't be there.
Just like the frog starving amidst the dead flies because its model says food moves.
Precisely. As these systems get smarter and their internal models get stronger, the risk isn't just that they miss things, it's that they might start seeing the world they expect, rather than the world that is.
That is a terrifying thought.
Yeah?
The machine might be driving us off a cliff because its internal map says there's a bridge.
Let's just hope the engineers get that balance right.
Indeed. On that slightly unsettling note, that wraps up our deep dive into the machine's eye view. Thanks for listening, and we'll see you in the next one.